The stuff you should have seen up until now is policy iteration, value iteration, this representation of how we define the value of being in a certain state and taking a certain action and deciding if that was a good state to be in, which we can use to figure out if the policy we're kind of implicitly following now in that value function is good or not, right? And so as we go forward, we're going to get more and more explicit representations of the policy, but the value function is still kind of that core. And this generalized policy iteration method is kind of underlying all of this, where we have, you know, the policy and the value function, and we kind of evaluate. I draw this picture kind of a bunch of times now in the later lecture, and we kind of maximize or greedily evaluate this this value function. So that's the end of my screen. Right, so we've got this loop of generalized policy iteration where we're kind of improving our policy by using our estimates all the time. I don't know if I showed you this picture before, so we're going to see it. You see it in the other lectures I'll post, but this kind of a view that they're using in the textbook, and I think it's pretty useful for seeing all the different ranges of stuff. So what we've seen so far is kind of in this range, right? So you've got PI here, and VI, and asynchronous policy iteration. They do exact optimization of the policies, and they're using that value function directly, right? So what we're going to talk about right now is this Monte Carlo thing, where instead of doing exact across the entire tree, we're going to dig down, use random sampling, and try to estimate the same things, but in an approximate manner. And then the videos are this. We're just going to give a little summary of the basics of this, and then this temporal difference thing is kind of where a lot of our time will be spent from now on. This exhaustive search area we're not really touching because this is kind of where control theory and other AI algorithms, A-star and planning kind of come from, and exhaustively search through things, and tree search. So I think you have other courses on that. We do swing back to it a bit when we talk about AlphaGo, because combining all these together is one of the things that people are doing these days. But just this Monte Carlo method approach we're talking about right now. Monte Carlo, if you don't know, and if you don't watch enough James Bond movies, the Monte Carlo casino, and so methods that use randomized choices or samples are often called Monte Carlo methods. So in machine learning, there's Monte Carlo Markov chain methods, which are quite useful in many areas. And it really usually boils down to drawing random samples from some distribution and using that to build estimating, to learn, to do optimization. So these are Monte Carlo methods for reinforcement learning, which means we can do some random sampling and use that to build our value function. We're still building from our experience, so the agent kind of takes some actions, figure out what happens, and then uses that to update their value using the rewards they saw. There's two different, the reason I want to go through this, because we may not use these methods that much. Other algorithms kind of build on this Monte Carlo idea. This chapter 5, covers Monte Carlo methods deeply in the textbook, and sort of uses them as its own solution, and that doesn't really happen that often that you use a pure Monte Carlo algorithm, but they're the first place we see some of these concepts to introduce, and the idea of randomness we are going to use. So we could have this first time we see these two concepts of model-free or simulated, because what we're talking about when we say model in RL, well, model is a very overloaded word. I try to make sure my students hardly ever use it because every field of science means something different. In RL, we're talking about usually the dynamics, right? And so it's this probability function that goes from a state and an action to another state, right? If it's deterministic, it gives you the next state. If it's probabilistic, then it goes from SA and actually gives you a probability, right? So that's the model, and we've in dynamic programming we assumed that we have the model, right? We always have p. That's how we solve it. We have a system of equations. You can solve for the variables exactly, or you can kind of do this iterative update, but you still assume that p is given to you, right? So now we're going to assume the model is not given, and so there's two ways to do this with Monte Carlo. You can say there's no model at all, and it just kind of learns the policy from its own experience. Or it uses a simulation that it can query, so it can ask this a question and get the probability out or the next state, but it's not given the actual definition, so it can't just ask it for arbitrary states. One thing that's weird with the Monte Carlo methods that other ones won't use that much is that they're going to do the complete returns, and I'll make more sense when we show an example, but it comes down to saying that you have to play the game to the end or let your agent run until a certain point, and then you get to update. So those returns you're computing for assignment 1, you can't get the return until you get to the end of some game, and then you update your value function. We actually usually want to be more incremental, but Monte Carlo, you have to wait till the end. That's one of the major properties of it. And then we also have this idea of saying that you have to be on policy or off policy, which we'll explain when we look at the algorithm. So are you updating your values based on the policy you're using, or are you updating it based on some other policy? So why would you do that? That's actually a useful concept in a lot of RL. So what is Monte Carlo policy evaluation, right? So here we're not taking actions yet. We'll have actions first, later. But here we're still just basically trying to estimate VS or QSA, right? Rather than actually choosing it. So we assume we're given some policy, which says here's how you will behave, here's the rule that you're given, and then we want to learn the value function for that policy for the start state or any state. And the idea is you have a Markov chain, a chain of states. You're in some state, and then you take an action, and then you end up in another state based on the environment, right? And you sample actions from that policy, and at the end you get to some return, and that's what you're going to use to update your value function. So it sounds the same as what we've been thinking about with dynamic programming, but there's a subtle difference here, is that, which we'll see, because we're not exploring all the possibilities, right? We're just taking one sample through the possible things you could do and moving forward. So every visit versus first visit. This is a bit of a subtlety of like, do you update? So S is a particular state, right? But S is one of the states in S here, and S is, in this case, got 5 states, right? And we know that number 5 is the terminal state. So the question is, do you update? Here we, in this history, this is like a trajectory, we ended up going, say, in this way, right? So this is a series of events that we had in this run. We had 1, 2, 3, then 2, then 3, then 4, and then 5, and we stopped, right? And then we got a reward, and then we updated all the states for all S in S, right? So the question is, when you update 2, because say 2 and 3, you're visiting them more than once, do you use the return you would have got just from the first time you got there, or from all the times you got there? That's what this distinction is talking about, which we'll see. There's just basically 2 different ways to compute that. So the simple kind of version of the policy is we're given this policy, we initialize our value function to some initial thing, and we have an initial kind of return. So we're keeping track of the return for every state, which is all the values you've gotten for ever being in that state. So whenever you're in state S, which could have been 1, at some point you went forward and got all these things and you got a return, right? And then another time you went off this way and you compute other things and you got another return, right? And so this returns S is something you're just going to keep adding, right? So we're pending this return here. And of course, as you guys are doing in your assignment, right, when you compute this return here, you're actually discounting it probably, depending on the definition. So we're just adding returns to this list, and then the updating is to average all of them. So it's kind of the most basic thing you could do, just taking those computations you're using for dynamic programming, storing them, and then doing them kind of in batch form later. So the way this compares to dynamic programming is in dynamic programming, right, we can choose any state we want because we know P, right, we know the dynamics. We can basically go through every state, go through it lots of times until we have a really good estimate, jump to some other states, and we do them in this table, right? That's why we have dynamic programming. We have a table for all the states, and we just fill them in using our best guess, our current value estimate of the values of the other states, right? So when we're updating this one, if this is st plus 1 in this particular case, we're using the value from here, and then that depends on the value from this state, right? And as we get better, we kind of keep cycling back and forth until we've stopped changing. That's what that generalized policy iteration kind of convergence is. But in contrast, in Monte Carlo method, we're not going across this entire tree. We don't have P. We just go down a particular track, right? So we follow the policy and sample from it, and we get a series of actions. And at the end here, we get some kind of reward. Well, actually, a series of rewards, right? We get R1, we get R2. And from that, we can compute our return, right? And the return is G, which is that function that you compute for every state. And so we only update this once we get to the end and we get the reward, and then we can update it all together. So that's kind of the basic approach. So it's really kind of depth first search versus breadth first search, right? Back from your 108 or 208 courses. How do you, what's the better approach? They have their pros and cons. This one is able to get you deep estimates of particular policies, but obviously you're missing lots of opportunities, right? So it's hard to get to, you would think it's hard to get to the optimal solution here because you might be missing something really good. Whereas in dynamic programming, you're explicitly exploring everything. When you get to the end, you've got the optimal solution. And there actually are guarantees about Monte Carlo being able to give you optimality, but you have to make certain assumptions. So there's a couple examples in the text which you guys can look at. This one, I guess, is pretty simple to explain, so I'll kind of do that briefly. I want to finish this Monte Carlo thing in this session and kind of give you the highlights. Yeah, this is still a core part. So Blackjack. Do you know Blackjack? Everyone know how to play Blackjack? It's 21. Much simpler than poker, right? The idea is you have you get dealt 2 cards initially. I guess sometimes you get with 1 card and you draw more, but let's say you're given 2 cards initially, and then the goal is to get as close to 21 without going over and winning, right? So whoever gets closest to 21 wins. If you go over 21, you're bust and you're out. And the way you count the cards is the number is the number. Face cards are all 10, and aces can be 1 or 11. So it's a choice you have. When you have the ace, you can, at any point before you finish, you can call it a 1 or 11. So that's a critical kind of decision. So the only the state here is the cards in your hand, right, and what they add up to. It's really just the sum of the numbers of your hand, and you also know something about 1 card the dealer has up. So this idea of usable ace, so that's a kind of a particular feature of this domain, is that obviously if you've got anything from 0 to 19, well, 1 to 19, you can use your ace for 1, right? But if it's if you're below 10, your ace could be an 11, and then you get to 21, right? I don't know what I'm trying to draw here. It's about the aces. Right, so you've got kind of different decision points here. Whereas you've got 2 things you can do, right? You can draw another card or stop. And you also have this, I guess, choice about what to use for the ace, but that kind of is automatic. So you get to decide whether you're going to draw another card or not, right? And so if you're in this area and you don't have an ace, you should obviously draw another card, right? Because you can't go over 20, 21. If you're in this area and you have an ace, maybe you could make it up or down so you can take this chance, right? And if you're in these areas, maybe you should just stop, right? Because you've already at the end. So that's essentially the entire game. And the policy, I guess, do we show the policy? Yeah, the policy we're doing here is essentially exactly what I was saying. That if you're in the last two, if you've got a 20 or 21 as your sum, you stop. Otherwise, you draw a card. But you have to keep track of whether when you're lower, if your ace is going to go over. And so when you run this game and try to play it and optimize it using Monte Carlo, you can kind of train it and see how well it improves, right? So after 10,000 plays of this game, and this is going to be a problem with RL, a lot of times you have to basically train it a lot to learn anything, even though it seems like a small game, but there's a lot of cards. There's two different scenarios, right? So it has to have a value function for if your ace can be used as an 11 or not, right? Usable ace is whether the ace would bring you over 11 or not, bring you over 21 or not. So at the beginning it's got this very rough estimate, and then later on it gets this really good estimate, which is that the value of being in those states in 21, right? That's the values are here at 21. The values of being in those last two states is really good, and the values of being here is kind of lower, so you'd rather be there, right? So that's just what the value function is telling you. But it has to learn separate functions for whether the ace can bring you over or not. So an important part of how this works then is that it's just following a particular policy. So it has that policy that's given, and it's just trying to evaluate how good it is, right? You just try it out, and when you get the score at the end, you update your states, right? So remember in dynamic programming, we would always use that v value of the next state. So we're not using v st plus 1 in this at all, right? We're actually just waiting until we get the reward and then doing updates with the return directly. I think there's some formula later where we show that. But it still is useful if the model's not available, right? Because you don't basically have any kind of ability, nobody tells you the probability of this card coming up or not. All you have is the experience you're using, right? And there are results showing that it does converge, but you have to have this assumption that every state action pair is visited, right? So for a card game, that means every possible set of cards you could have, every possible score you could have, and combination of whether the ace is usable or not, you have to have a bunch of estimates for every one of those possible states. But as long as you do that, then it will converge eventually. So you have a guarantee there, even though it's completely kind of very stochastic and it's not doing this breadth first search. So it's nice that it has a guarantee that way. So there's different ways to try to to manage that and make sure that this is the ability, this is the true property of how you're using it, so that you can have this convergence. So one way to do that is exploring starts, right, where you say that start state, so where we are at the beginning, right, because this S here, S0, if you got dealt the same card every time, you would only explore that part of the tree, right? So and the next time you run it, it's going to go down another branch of the tree, and the next time you run it, it's going to go down a different branch of the tree. But if you say that, you randomize the cards, right, so it's going to be the 1 of hearts and the 2 of diamonds, and make sure that you randomize over all the cards uniformly, then eventually you'll explore all the states, right? Another thing they don't mention here is that it has to be true that every state is reachable. Right, so some state, if some states are not reachable eventually from every other state, then you can't kind of learn the entire system. And there's some restrictions on this, where they, like, not every other state, but if you have some states that you can't reach, so you definitely have here, and then there's other ones over here, so maybe some score, like 13 is your hand. If there's no way to get there, then you'd never be able to learn that one, right? So it could be all these ones, but maybe there's like completely disjoint sets of some of the values. If that's the property, then there'd be problems as well. So the main approach that we're following here is this policy iteration, generalized policy iteration approach, right? We've given a policy, we're estimating it. Just that evaluation method is doing this kind of depth first tree search evaluation of that policy. And many of the methods we're looking at are going to have this kind of structure where we're given a policy, we evaluate it, and then if we want to now take actions, we can kind of improve, update the policy, right? The policy we were given initially there was hold if it's 20 or 21 and draw a card otherwise. But you want to actually learn a better policy over time. Yeah, so this convergence of action values, right? This convergence of the action value function, not necessarily of control, but if the action value function converges, right? So your estimator of a particular policy converges, then your controller will converge as well, as long as it's always improving, right? So every time you evaluate it, if you're taking the greedy maximization of that value function you have, you're taking the best action you can, then the value of the optimal policy under the new value function should be higher than it was previously. So what they're updating the policy here, so you've actually changed the policy now. And as long as that's true in your domain, then you know it's going to converge to some policy that can't be kind of improved upon within that domain anyways. But there can be different, they converge at different points actually than other algorithms. So we'll see in the slides, the lectures I release tonight, which are on TD temporal difference methods. They kind of do a little bit of Monte Carlo randomization, but they also use the value function, the recursive kind of definition where you're backwards updating, and they can converge to different policies. But it's whether it converges to something is kind of what you're being asked about, right? Rather than it just kind of continuing to change forever. Is it going to converge to anything? What else do we have here? So this idea with the exploring starts, kind of have it written out as an algorithm to make sure that it's exploring the space fully and the starting states. What's interesting here? So it's got this same kind of idea that we're starting with some given policy and value function, which is randomly kind of set them up. And then the loop for improving the policy here is the same as dynamic programming and the temporal difference things. You've got a value function that you're updating, but the difference is going to be that you're not using the individual reward here. You're waiting until you get an entire return, and then you're averaging it over all the returns you've seen, right? So like I said before, you're starting at some start state, and the first run you go off and you do this and you get some reward, right? And then the second time you go there and you get some reward. And so the return is being computed. It's going to be the G's that are derived from each of these, G1, G2, over time. It's just going to be an array of these. Sorry, I'm on the end of my screen here. The returns array that we're talking about down there contains all of these, right? So it's basically the history of all the different scenarios you've run through, and you're averaging those to get your evaluation, and then you maximize that Q to get your policy, right? And I don't remember if we've talked about that or it's in the future, right? To update your policy, you could either create a table that has a reference and stores that, or you just say that policy for a state is the function which does this, right? So when you need to take an action, right, here we're generating one of these rollouts. At many points during that rollout, you have to take an action, right? How do you take an action? You call the policy function, you tell it your current state, and you do argmax on your current Q value, right? You could represent this as a table and do it all for all the states, but there's no need to because you have Q already as a table, and you essentially have to just find that state and look up all the actions and pick the maximum one. So this is an assignment in the kind of pure pseudocode, but programmatically, you don't need to write down that. You don't need to store this pi as long as you have Q stored, which is important when you're talking about coding it, which you'll see for the next assignment. We'll give you kind of a template for how you do that, but that's the idea. You want to store this Q and keep updating it, and then when you need to take an action, you just look it up in a particular way. So there's more analysis of that Blackjack example. I don't think that's so interesting. Okay, so there's on policy, off policy thing. It's important. So this is saying that whether you're using the policy that, I mean, how could you go off policy? So let's explain on policy first, because it seems like obvious. You have a policy. The policy is derived from your value function, right? And you're deciding how to play blackjack or move your robot around the room. The goal, what we want to do here is get rid of exploring starts. What are we saying here? Okay, yeah, so an alternative way to say, we don't want to randomize over all possible start states just to make sure we have this convergence property. What's another way to do it? Well, we could say that the policy keeps getting updated, but we're going to put this constraint on the policy such that it can never go to 0. Nothing is impossible, right? So every action that is available to you is always available, and no matter how much you learn, you'll never let it go to 0. If that's true, and you're randomly sampling that policy, then eventually you'll still visit all the states, right? So this is called an epsilon soft policy, and you can define it in many different ways, but you basically say, normalize over all the actions. So A, I guess fancy A here is meaning all the actions that are available in this particular state, and epsilon is some small number, and you have different ways of getting this, but you basically want to build a probability function that tells you the odds of either choosing the action based on your value function or choosing some other one. If you never let that probability go to 0 of a random choice, then it'll be epsilon greedy. So using this, we're still kind of always moving towards a better policy, and it will converge to the best possible policy that is of this form, right? Because maybe there's an optimal policy with zeros in it that is actually better, right? Because some states really are horrible. You should never go to them. So you'll have an optimal epsilon soft policy, but the value of not the normal policy that has zeros in it might actually be higher, right? So it's optimal, but only optimal within these constraints. So on policy here is like we were saying, you're learning Q, and when you take an action, where's the action? Return for each pair, generate an episode. So it's kind of hidden, right, in the code. But generating an episode using pi, right, because pi is defined as set of A, using it. So you have to follow the chain here to realize that pi depends on A. Right, but it depends on A, which depends on Q, right? That means you're on policy, right? You're using your actual value function to decide what action you should take. There's another way to do this where you could say, I'm going to use some other policy to update my values, not the one that I'm going to actually act on, right? So we could have, we'll call them the target policy, which is the one we've been talking about up until now, and we'll have the behavior policy. Right, so target policy is what we're learning, and behavior policy is actually what we do, right? So what we learn is the target policy, and what we do is the behavior policy. So it's kind of like do as I say, not as I do. That's this method here, where you do something different, even though you tell people to do something a certain way. And there's a good reason to do this, though, because it helps you explore the world differently. So B could be this exploratory thing, this epsilon soft that never goes to 0, and it makes sure that you adhere to this constraint that lets you explore the entire state space. Um, it That's just one possibility. Uh, and then but then in that case, then the policy that you're using for updating your value function could be the purely greedy one, right? Because you really want to learn the best policy, but when you get to the real world, you'll always have this chance that you're going to do something suboptimal because you need to keep exploring just in case you miss something. That's the idea. But then this means you're off policy because you've got two different policies. One which is you're using for learning, and one which is using for acting. Oh, okay. We don't want the prediction one. So, so this slide 25 um, is the off policy kind of implementation. So same thing. We start off with the value function. Ignoring this kind of weight, I mean, before we have a kind of a weight of alpha here that kind of tells us how important that update should be. Now we're weighting that based on the number of samples we've seen, so we can kind of double back and look at that. But we're still using this return, right? So we've got the return we've gained from following out the policy when we get to the end of the trajectory. And then we update pi using argmax, right? So we're taking the best possible action from Q. This isn't epsilon greedy, this isn't anything, just say pick the best action and make the new policy that, and then keep going. But then when we generate the episode, we're using some other policy B, right? And B, we just said any soft policy. B could be, my mouse is frozen. Right, so the idea is that this soft policy here then would be that epsilon soft policy we talked about that never goes to zero. And in the part where you're generating the trajectory, choosing the action, you'd use that. And so you've generated a history with one policy, but when you decide to learn from that, you assume that the value that you would have that you obtained is the optimal one. So you're updating the policy that way, and then pi gets stored. I'm trying to see where they use pi here. I guess you're not really using it. Yeah, so in SARSA, it becomes SARSA and Q learning. We see this again. So in the next set of lecture that's coming out tonight, this concept comes up again, but it's a bit more clear because here, in that case, you actually take the sample and the actions in each case. But here we're generating an entire series of actions using this other policy, but then we kind of just save our optimal pi but never use it, right? We just decide the exit condition here is to say that the policy has stopped changing, right? So we do keep track of what action we did last time, and if it didn't change, then for all the actions, all the states, then we stop. Yeah, the idea is that you can use two different things. And so the reason we do that is because you're trying to explore differently, right? And so, oh, this moved, eh? Yeah, I was just skipping over this important sampling part, kind of in the interest of time. So with this Monte Carlo thing, then comparison to dynamic programming, it gives us a different way of exploring that, right? So it's not using this what they call bootstrapping, what I'm often calling recursion, or well, recursion. I say recursion, but that's the fact that you're using another value in your pre-computed value for that state. Monte Carlo, you wait until you get the actual returns and then just use that to update. But it uses sampling, and so it lets you kind of go through the space more efficiently, whereas dynamic programming doesn't do that. But in order for it to still converge and get you the answer eventually, you can sample, but you have to promise that you'll sample everything eventually. And there's various different tricks to make sure you do that. And this important sampling stuff is basically a way to try to do that with more efficiently without having to really sample everything, but by weighting them down and saying, well, how important are they? We'll visit them eventually, but if they're more important, we'll weight them heavier. So if we come back to that in another algorithm later, we can kind of show it up. But like I said, Monte Carlo methods purely on their own are not something that we use a lot. They are a basis that we use for temporal difference methods and other things, which is the next lecture, which I'll come up very soon. What other facts did they want to put in here? On policy versus off policy, and this sampling versus not sampling are kind of the main parts. Yeah, and I guess a main thing is that Monte Carlo methods, they're really learning from their experience, so they're not taking advantage of anything they've learned about future states they could be in from other parts of the value function. They only learn about things they literally did in that pass, right? So in a way, it's only learning about the past experiences, whereas methods that use dynamic programming in some form, even if they're stochastic, can use what they believe about the future in terms of that agent making actions. So that's why they kind of be more powerful. But combining these two together is what we're going to use with temporal differences, which is this week as well. So like I said, this is a sampling of some of the topics from chapter 5 that are useful, and things I glossed over here you can consider glossed over in terms of evaluation, unless I explicitly come back to it, but they are interesting as well, so you can kind of look into them and we can talk about it. So I'll end it there, and if there's any questions, I'll give you a few moments. Otherwise, that's where we'll stop. And like I said, there'll be a bunch more stuff coming out for you guys to work on, and good luck with the final part of your assignment. And hope all your other courses are going well, enjoying some of the sunshine when you get a chance.